Hi, everybody. My name is Dave Springer. This is the Beyond JavaScript session. We're going to talk about how to bring your client code to the web. So wouldn't it be awesome if you could take client apps and serve them on the web as a web app? And that's what we're going to talk about today, how we can do that. Quick show of hands, how many people here are client programmers versus web programmers? For client programmers, we got, that's okay. And then web programmers, pretty much everybody else. So that's half and half, awesome. All right, good, so I got a little something for everybody. I am the tech lead of the Native Client SDK group out in Boulder, Colorado. And we are building the SDK on top of the native client technology. Today, we'll talk about the technology itself, quick overview. I'm not going to do like a really super deep dive into that. It's just more of a, hey, this is what we can do with it. This idea that we can merge these two worlds of web programming and client programming and talk about how we can bring that native code into the web. I'm going to go through a couple use cases, what native client is really good at. There's this idea of a 90-10 application where 90% of your app is in web programming, 10% in native code, versus the 10-90, which is where nearly all of it is in the native code. 10% is in the web and 90% is in the native code. And we're going to build an app right here, live on stage. Write code and compile it and run it. Okay, and then we'll go through Q&A. So what is NACL? We abbreviate everything, you know. So native client is shortened to NACL. This gives way to all kinds of bad puns on salt and pepper and, right, NACL. Okay, everybody got that? Good, all right. Good to keep up. It is a sandboxing technology for the safe and execution native code. That means it's as safe as JavaScript. So today you're running your JavaScript in a sandbox. We're providing another sandbox in addition to that one to actually run your native code. It is real CPU instructions. It's machine code running on the native CPU. It's not an interpreter. You can do things in it. So we provide a kind of a POSIX-like API, and I'll talk a little bit more about that in a second. And we also provide this pepper API, goes with salt. So it's the way that you talk to the browser, and again, we'll get into that a little bit more later. It's a technology that helps you merge all the benefits of web programming. So this, you know, you're programming the web, you write it once, and it runs everywhere. It doesn't matter what platform it's running on, as long as it has a browser, you can run a web app. So we merge that delivery promise with native code. So it's this idea that you write your native code once, you build it, and serve it as a web app, and it runs on all platforms that have a browser. There are restrictions. Okay? So the idea is we want everything to be as secure as JavaScript. So if you were here in other sessions, for example, the fireside chat just before this one, we talked a lot about security. So we're pretty uptight about it. And we want things to be safe, even though you're running native code, which can potentially be quite dangerous. So how does this all work? First of all, you take your source code, which might be, say, C or C++, and you have to compile it. So we've provided specialized tool chains. They're based on GCC, and we've modified them slightly. And what happens is you build for specific CPU architectures. Obviously, you are running machine instructions, so that means you have to compile for specific architectures, x86-32 versus x86-64 versus ARM, for example. Once you've built and linked an executable from your source code, then we do a static analysis on it to make sure that your code isn't doing something naughty. You know, so we look at we'll get into an example of that in a second. And that's a static analysis phase. So if the code passes a static analysis phase and it's okay, then it goes inside of our sandbox to be run. And the sandbox actually lives inside the browser. Today we live inside Chrome. So again, not an interpreter, but the sandbox, if you try to do nasty things at runtime, then the sandbox attempts to catch those and halt the malicious code. So we don't actually prevent malicious code from getting into your browser, but we do our best to stop it if it gets there and tries to do naughty stuff. So these are some of the restrictions that I alluded to earlier. You can't directly touch the file system of the client computer. You can't do open, stat, things like that. You cannot fork off a process, obviously. That would be bad. You can't kill things. You can get a complete list of all the disallowed system calls from libnosis.a. That all comes in the SDK. If you download it, and at the end you'll see a link of where to get that. So how does it work? You start with the browser, of course, which has its own sandbox. And this is executing your markup, your CSS, or JavaScript, et cetera. There is a bridge, the Pepper API, and this is how the JavaScript in the browser talks to the native code in the NACL sandbox. And then there's the NACL sandbox, which is this runtime that's actually running your native code. Okay. And as we go through all the examples, you'll see this graphic, and it'll show when I'm in the browser, when I'm on the Pepper bridge, when I'm in the NACL code, and that'll make sense when you see that. So how do we do things with our special toolchain invalidator? So who can spot the evil code here? Hint: there's at least 4 instructions in here that are bad. So for example, every memory access and control transfer is potentially unsafe. All right? So things like this jump has to go to a valid address. So this is all things we can find out during static analysis. And this call, x86, for example, has a variable length instruction word. So that means this call can jump back into the middle of an instruction and start executing bad stuff. Right? So we don't want to do that. We don't want to allow that. So what we do is, in this case of the call, we say that we require a 32-byte aligned jump. We also do things like we give you a fixed amount of memory space to work in. You have 4 gigs, and you can't go outside of that. You can make system calls, and we have this idea of a trampoline. So in your native client code that's built with a special tool chain, it's all validated. Let's say you want to call mmap. So first thing that happens is that gets bundled up with its parameters and pushed through a trampoline into what we call the trusted code, which is our sandbox, our NACL runtime that's built into the browser. This goes through a dispatcher, which looks at all the parameters and makes sure that, for example, you're mmapping a legal amount of memory, and that your addresses you're trying to mmap are okay, that they're within range, that the descriptor you're trying to map to is a valid descriptor that you got from the untrusted libraries and so on. Then if that's all okay, we turn that into the actual real syscall that calls to the operating system and does the mmap. That gets a return value, which then goes into the springboard, back to your untrusted code, and off you go. So if at any time during that chain of events something goes wrong or it looks bad, your code is halted. And a halt, by the way, looks like a snap, right? I mean, the thing just stops. So we call this security model defense in depth. It's kind of akin to, let's say you bought something really valuable. You might take that valuable thing and put it in a really big safe. But you probably wouldn't take that safe and just leave it in a vacant lot in the Tenderloin. what you would probably do is put the safe in your basement, behind a locked door, which has got an alarm system, and your front door has a lock, maybe a big dog, and things like that, right? So that's the kind of approach we're taking, is let's try and get as many layers, defensible layers as we can get between the native code and the OS. And we do this by, we have our own sandbox that runs native code. It runs alongside of the Chrome sandbox. So actually, malicious code has to get out of 2 sandboxes in order to try and do anything. It's pretty hard to do. We do things like implement cores. So our URL download HTTP request stuff all works with that. We can blacklist CPUs. Certain CPUs have instruction sets that are known to be buggy. So we can, it's pretty rare nowadays, but we can do that. You can blacklist NACL modules. So this is the same thing as blacklisting an URL, right? Because it just, as we'll see later, this is just a web app. So it's a URL, and you can blacklist those. Native Client is a open source project. So it's pretty, we do security audits, we have contests, we have public review of the code, we have peer reviews. We're really, really sensitive to the security issues and are trying to get the attack surface as small as possible. Okay, so why would you use native client? First of all, choice of language is a big deal, right? Let's say that you have a fairly large investment in C++ or C, one of these compiled languages for client code. And we hear a lot of people saying they would rather not translate all of that into JavaScript, especially if you have many hundreds of thousands of lines of code. It can be quite a burden. So now you can compile it with our tool chain and with what turns out often the case is a fairly unchallenging porting effort. You can run the whole thing inside of native client. Maybe you have some performance considerations to think about. Native client does give you direct access to the CPU and GPU. You can take advantage of SIMD instructions. So for example, if you have SSE3 in your app, then you can hand code that kind of assembly language, as long as it is within our validator rules, and most of them are. You can take advantage of multi-core CPUs. We implement the Pthreads library, so you can run multiple threads. And actually, in my example, I'll show what happens when you do that and the kind of performance improvement you can get by getting off the main browser thread. And again, if you're writing in a language such as C or C++, where you can do things like dereference pointers, and that's important and it gives you the speed, then you can lay out your data and you can do that. That's not something that's very easy to do within JavaScript. And finally, this gives your client code the browser as the delivery platform. So it's no more that you have to opt into a lengthy download or hard media. Basically, there is a frictionless install, as if there's no user install. There's no opting into trusted code and do you trust this site and so on and so forth. There's none of that. You just simply serve the NACL module as part of your website. That's it. So it's the end of this stuff, right? Plus, because it's a website, you're also in the Chrome Web Store, which is a plus. So let's talk a little bit about the 9010 versus 1090 style applications. The 9010 application, again, is just 90% of your app is in web code. What we call it's a web app. In other words, it's markup, it's CSS, it's JavaScript. 10% is native client versus the other way around, which is that very, very little of the code is actually in the web, and most of it's in the native code. So a 9010 application, is usually a web-centric app, and it needs some kind of an engine that wants to take advantage of things like data layout, multi-threading, and so on and so forth. It's kind of the situation where you want to have a very low latency local server. You can think of it that way. An example might be crypto, right? So you want to implement a DRM solution using your specific crypto IP. And you can do this now with native client because your crypto technology, you can just stick it in the browser as part of the web experience and ship your encrypted data back and forth across the wire. Another example might be a physics engine. So you've got most of your game programmed as a web app, but you want to run a physics engine and actually look at data in a certain way. Again, a great example, this is a 9010 use of NACL. A 1090 application might be where you have a very big investment already in C and C++ code, let's say, and you've implemented the whole UI and the game experience, for example, in that language. So this is where you just need a very thin shim, basically just the thinnest possible delivery platform to connect into the browser, but then actually deliver your entire game as if it was one big client app. So that's also possible to do. Great application of native client. Okay, let's get down to building an app now. We're going to build the game of life. It's Conway's life simulation. And we'll go through this in 4 stages. So the first stage, we'll get started. And for you client programmers out there, what we're doing is building a website. We're not building client apps anymore as such. We're building websites now. So I'm going to go through kind of those steps because it's a little bit different. It's a little bit different delivery mechanism than perhaps what you're used to if you're a client programmer. It's no more just a .exe that somebody runs. It's now you have to go to a website and there's resources that you serve. And then we'll talk about how to integrate with the browser. So this is getting the JavaScript to talk to the native code. And that gets a little tricky because the interfaces are all asynchronous. If you're used to the kind of programming where you make a function call and then you get a return value, that doesn't exist anymore. So I'm going to get into that a little bit because it can be new to some. Then we'll optimize by using multiple threads. I'll show you how easy that is to do. It's one of these things where I just make some changes in the back-end code and everything gets faster. And then to wrap up, just show a couple of the other interfaces that we have implemented, audio, HTTP requests, things like that, and we'll add sound files to this game. It's a little gratuitous, but it's fun. Okay, first stage. This is where we're going to lay out the project. Again, we're building a website, so there's more involved than just build scripts and CC files for you client programmers. For you web programmers, this is going to look absolutely boring and normal, except for the fact that there are also .cc files and stuff that has to be run through the compiler. So that's a little bit different. It's kind of this merging of these two worlds. Part of the SDK that we've built, we give you some scripts to help you lay out these projects. So it just kind of lays out some simple files that get you started. It gives you a build script that will run the special tool chains. It gets you started with a simple kind of .cc file that has the hooks to connect to the browser. And then what we'll do is why don't I just do it? We'll just run the script and make a simple project and see what goes on. Okay. So here I am in the SDK. And if I go into project templates, I can say init project.py. So I'll give it a name, is life 2011. Whoa. Okay. And then directory equals examples. Okay. So it just laid everything out for me. Now, if I go up into here, examples, life 2011, there's my simple template files. We use scons for our build system because it's kind of common among, all you need is Python. It doesn't require things like Sigma on Windows and so on and so forth, so it's just, that works. So if I say scons right now and just build it, here it is running the tool chain, and it's generated an NMF file, which I'll get into the details of that in a second. It's produced the NACL modules, a 32-bit one here, and a 64-bit one for me. So now I have my whole native client website. It's there. It doesn't really do very much, but it's workable. So what I'll do is run a little local, simple Python HTTP server, and we'll see what that website does right now. So if I run that, and then whip over to Chrome. This is, by the way, Chrome M11 stable, and native client is behind a flag. So we can go into about flags and see that native client is here. So it's something you have to actively enable because it's experimental still. Okay, so let me go to localhost 5103 life 2011. Oh, you can see I've done this before. Okay, so there it is. I just loaded my native client module, and it's running. Promise, it really is. It's not really doing anything, but there it is, done. Okay, so that was it. And you can see here, and the server is outputting that it actually, did some GET requests and so on and so forth. Okay, so that was it. And to go through the kind of files you get, there's an HTML template, there's this NMF, it's a manifest file, and we'll talk a bit more about that. That's how you actually glue the architecture-specific nexes into the browser. And that's how the native client runtime knows which architecture to pull in and run. Okay, then it makes the nexe files, of course, and then there's just some other stuff in there, some CSS that I have in an image. Okay, so let's take a look at this actual code. I'm in the browser now, and you can see I've highlighted the browser piece of the graphic there. This is how we do it. Embed tag, it's that simple. And we give it the source of this NMF file, which is a little piece of JSON, and we'll see that next slide, what that exactly looks like. That's the thing, the NMF file is the thing that actually ties the NACL modules that you built from native code into the native client runtime. We tell it its MIME type is an application, it's of type NACL. And this is just some JavaScript-y stuff that I have that makes the embed tag expand to fill its tab. So this is how I'm kind of faking out a full tab game. Okay. This is the NMF file. It's just a little piece of JSON, and it says I want to map x86-64 architecture to this specific nexe. x86-32, the other one, and so on. Okay. So this goes into the runtime. The runtime knows how to figure out what kind of CPU architecture you're actually running on, and then it goes and makes a request for the specific nexe it needs to run. That's how we gain our platform independence, right? So yes, you have to build a nexe for each architecture you want to run on today, but we do our best to make that all invisible to the user. Okay. In the life example, we're going to do some 2D graphics. This is akin to using the canvas tag. And this is programming on the Pepper Bridge now. So this is in C++ code in the Pepper Bridge. As in HTML5, you would use a canvas tag. In Pepper, we say, I want to make a new 2D context. And then I have a paint API, and I can flush it. So it's fairly straightforward. All right, let's see what that looks like. I have here a pre-baked version of that website. So here it is running. And that's Conway's life simulation. And I can go and say enter full screen mode. So that's that little piece of JavaScript. All I did was tell basically the 2D graphics context to expand itself to fill the whole screen. Okay. So that's pretty simple, right? I mean, it didn't really do anything except just run the simulation. What's actually going on under the hood there is the simulation itself was all completely programmed in native code. So that was all basically C++ code running the simulation, making the little automaton. And the toolbar, the area where it was running in, and the thing along the bottom, that was all web programming. That was all JavaScript and markup. Okay, so let's get a little more interesting. We're going to turn this into an actual web application, kind of a little more of a game. And what we'll do, for example, we'll go back into the browser again now and start writing in markup in JavaScript and do things like write a little stamp editor. So those of you who are familiar with Conway's life, you can give it initial values to do things like glider guns and puffer trains and fish and things like that. So we can add a bunch of JavaScript to implement this panel. We'll add some buttons. So we can run it in that random mode where it just gives you a bunch of initial values randomly versus actually stamping them down. And then we can also change the automaton rules. Excuse me. Okay, so this is kind of, for you web programmers out there, this is just absolutely everyday markup, right? Nothing special here, a bunch of JavaScript to implement the panel. By the way, in this example, I'm using a lot of Google Closure. That's not necessary. I work for Google, so it's easy. But jQuery, Prototype, there's many, many JavaScript libraries out there, as you know. So one of the things I want to do is actually be able to click these stamps down and then drag them along, all right? So I'm going to add that and process drag events. I'm going to use Closure for that because it's really simple. And we'll talk about how to connect the fact that I've made a mouse down to add a stamp, connect that from the JavaScript through the C++. So I'm going to kind of get into that in a little detail because that's sort of, because it's asynchronous and it's maybe not familiar to everybody. We'll look at the Pepper interface and the post message style JavaScript interface that we use. And then we'll actually work through an example and add a clear button. Okay, so first of all, in the browser, I want to add dragger if it's simple, right? I just GoogFX dragger, that's Closure, done. It does the usual thing of listen for mouse down, mouse move, mouse up, and turns them into drag events. I have in my view controller code, I have a listener that I hook up to those events and give it handlers. And in the handler, all I do is I say, OK, I'm going to handle the event, stop propagating it. And then I'm going to invoke the put stamp at point method on my native client module. And this is where we're going to get into the bridging. So a little bit about how this app is set up. The embed tag that you saw earlier is actually represented by a JavaScript object that I call a view controller. And it owns the DOM element, which is the native client module. So it appears to the browser kind of like a JavaScript object that implements certain things, such as post message. Okay, so here is the implementation of my invoke method. Now you can make this as arbitrarily complex as you want. I just build a simple colon-separated string of method name and parameters. You could use JSON stringify for this, but then of course you would have JSON going into C++ code, so then in the C++ side, and you'll see that later, you would have to unroll all the JSON. This is just really, really simple for me to do. And how I get it into the NACL module is I just call post message on the DOM element itself. So there's a DOM element that represents the NACL module. I call post message, and off it goes. Now here's where the asynchronous stuff happens, right? Because this post message returns immediately. So there's no waiting. It just pushes the message out to the NACL module and returns. It just sort of hopes it gets there. There is a way to do closures and close that loop. I don't have it in this example, but you can post message back from the C++ to the browser. So if I wanted to have a closure here that did something when the value actually got to the C++ and got processed, I could do that. This example doesn't have it. So a little quick word on how this all works. This is for you client guys that are maybe used to saying, oh, well, I just call a method and it does something and then returns. That doesn't happen anymore. What goes on now is that I say post message from JavaScript. That puts that post message command with its parameter. It actually copies it by value. So the entire contents of the post message call get copied. So you can return and start modifying it, but that copy is now on the pepper queue, waiting to be processed by the NACL module. Then later on, the NACL sandbox, which is running, picks that post message up with its data and calls handle message inside of the Pepper API. So the Pepper API is something that I have to implement. It's a bunch of known call points inside my C++ code. And I then am responsible for implementing handle message, picking up that string and parsing it and doing whatever. And we'll see how that works. So here I am on the Pepper bridge implementing handle message. So this is the other end of the post message. So post message happened in the browser. It copied the data. It put it on the Pepper queue and returned. So the browser's now off and running again. Now here I am in the NACL module in the Pepper bridge, and I get it's a variant. And I say, well, if it's a string, then I'm going to do the mirror in the C++ of invoke method. Right? So I just pull the string value off and call my scripting bridge. And this is something that actually I wrote in the NACL code. So this is my own thing. Again, right? It's the inverse of what I did in the JavaScript. In the JavaScript, I built up a string of colon-separated parameters. This is C++ that takes the string apart and builds basically a dictionary of the values. And then here I just simply invoke a callback in C++ with that parameter dictionary. Okay, so we'll add a clear button. We'll kind of go through this whole process. And this is where I'm going to really write code and compile it and stuff. It's often worked. Okay, so we'll add a clear button. The first thing we'll do is actually, we'll add the clear button in the markup, right? You web programmers, totally easy. Use button inside of a form, not hard. Then we'll wire up the on-click event on that button using JavaScript. And that'll bubble through into the view controller, which owns the NACL module DOM element, and actually finally do the post message of the clear method. And then we'll add a handler in C++ for that. So you see the whole process start to finish. Okay, so let's start with, here is what we've got. So here's this whole browser stamp editor, right? I mean, it's arbitrarily whatever. So I can make these stamps. I can run the simulation, and it's doing that kind of thing. So I did all the drag events. I can change the automaton rules. I don't know if everybody in the back can see, but it's way down at the bottom of the slide there, bottom of the screen. I can change the automaton rules so you can see what happens here. But of course, this is going to turn into a huge mess, and I can't clear this at all. So that's why I want to add the clear button. So let's do that right now. So what I do is go into my favorite text editor, and I have these little handy hooks here for me. The first thing I'm going to do is add the clear button. So if everybody can see that, this is just absolutely straightforward. HTML. And again, this is totally live, so all bets are off. All right, so I just put a clear button in there. It's a button that says clear. It's not exciting. Then what I want to do is go and wire up the on-click event. So I'm going to do that. Let me get this a little bit bigger so that we see the code. There we go. Okay. So I go into my JavaScript. And here I'm going to say, get the DOM element and add an event listener to it. And I want to call the clear event handler. So I better add an implementation for that so that it works. Let me put that there. Okay, so here's my clear event handler. Again, those of you used to web programming, this is totally normal. I just simply say stop propagating the event because I'm going to handle it, and I'm going to call the clear method on my view controller object. Now the view controller is not the NACL module yet. The view controller owns the NACL module, right? So I obviously have to also implement this clear method in my view controller. So I'm going to copy that and paste it into the view controller here. Okay, and you can see here it's calling invoke method of clear. Okay, so now I've done all the browser stuff. So let's see what that looks like. So if I go into my shell here and I'm handily in my life stage 2, I just say scons install. What that does is you see it's taken my HTML file that I edited, my JavaScript that I edited, and put it into my sites directory. By the way, on this Mac, I'm running a little Apache server, so I'm not using that simple HTTP server. It doesn't matter what your server is. You just have to have one. That's all. Okay. So let's see what happens there. So you remember what it looked like before. So that was a caching thing. Let me open this in an incognito window, and here's my clear button. Okay, so let me just run this in the random mode. Now I should be able to hit that button. Of course, it's not working. So why? Of course, I know why, but let's take a look at I can whip up developer tools here and look in my JavaScript code. Let me get rid of this. Pull that down here. I want to make sure that I'm actually getting the event handled correctly, right? So if I scroll down here to my implementation of clear. So I got a whole bunch of stuff. I'll put a breakpoint there on my clear button, and again run the simulation and hit the clear button, and sure enough, it is hitting it. So let me step over that and make sure it's indeed going into invoke method, and step into that, and it seems to be wanting to call post message with the clear method. Okay, so what hasn't happened yet, of course, is the C++ isn't there yet. So there's nothing on the other end to actually handle this clear. So let's go ahead and add that. Oops. Okay. Stop. Oh, I got to keep running. Haha. That's why it wasn't working. Okay, there was a fascinating little debugger demo. Now, so let's go ahead and add C++ code. So handily down here, I have some. Copy and go into C++. So if this is all set up right, I can paste it in there. And what's happening here is I have an implementation in the C++ code that will clear the buffers. It's this, the clear method. So here's what that looks like, where it's simply getting the pixel buffer that I've been painting in, and it clears it. And it clears the simulation buffers too, right? So that's all it's doing. and that piece of code that I pasted in there wires it up to the clear method. So that earlier C++ code you saw that unravels all the parameter names and so on and so forth, that's going to then call this. So let me save that. And now if I go in here and say scons install, you'll see that it's actually running the compiler now because it has to build C++ code. It's made new nexes and loaded them into my site. So let's take a look at what that looks like. And if I remember to do this in an incognito window again, let me run the simulation. Let's throw a couple little glider guns in there, and if I hit clear, it indeed clears. So let's go into stamp mode, clear, and then I can make a couple of glider guns in here like this, and stop the sim and clear, and it works. Okay, so that was kind of a deep dive into the whole JavaScript to C++. Okay, so we've connected those two things. Now let's make this go faster. Okay, so what I'm going to do is because I have the entire simulation programmed in C++, it's fairly straightforward to just simply take that implementation and run it on its own Pthread. The Pthread is running inside of native client code. And what that helps me do is get out of the browser's UI thread. Okay? So normally what's going on over the Pepper bridge is that as you make these post message calls and so on and so forth, it's all on one single browser thread. So it puts it on the Pepper queue, but then the runtime as it wants to paint things onto the 2D canvas that's shared with the browser, it has to do that on the browser's thread. So it has to actually stop the browser momentarily while it paints and come back. Okay? So what we're going to do is actually separate those two out onto separate threads and see what happens. And this is, so the promise is that you get this kind of UI snappiness, right, in your application. That's what you want. So I'm going to be working entirely in the native client code. There's going to be no front-end programming is required for this because all the wiring has already been done. And all I need to do now is just have a separate thread that runs the simulation. And here, this is where I do it. I just simply pthread create. So client programmers, normal, right? Stuff you're used to. Here's where I'm shutting the module down. I just simply join the thread, and we have mutices. And because it's just the full Pthread API and I'm programming in C code, I'm free to do things like make condition locks, right? So these are the kinds of things that are not generally available in worker threads in JavaScript. This is the full threading with mutices, with locks, with all that kind of stuff. So you can program points of synchronization in while the thread is running. It's not just start up and well it does what it does and then you don't hear from it again. You can do the full synchronization. I did a little kind of seat of the pants measuring. I'm getting about 6x performance improvement just by having one more thread. So it's quite remarkable. Okay, so let's see what that looks like. Actually, what I should be able to do is, let me go here, and if I reload, okay, so I'm going to put these side by side. Let me see if that'll work. I like to live on the edge. Okay, so here we have the old one. This is the single-threaded version. And here is the multi-threaded version. So single-threaded, multi-threaded. All right? So really, it's a remarkable difference. And that, again, is entirely via C++ code. There was no, whoops, ha, okay. Yeah. Did I mention this was live? Okay. Let's go through the fourth stage, which is we're just going to add some multimedia, okay, and go through what that's like. we're going to program on the Pepper bridge. It's in C++. So adding audio is kind of like using the audio tag in HTML, except not at all. So because with the audio tag, you say, you know, audio and give it an URL, and the browser figures out what kind of sound file you have, and it does all the decoding and all that kind of nice stuff. You have to do that yourself in Pepper. So that may seem daunting, and if all you really want to do is just simply play a sound, then using the audio tag is probably your best bet. However, if you want to do more with it, for example, do some processing to look at the sound and pull speech phonemes out and then give them timestamps so you can then do lip syncing and you know, that kind of processing, then this is absolutely perfect for that. So how we do it is as an HTML5, you have an audio tag. Here we just say I'm going to have an audio context. And the way it works is that it wants a callback that's going to fill buffers. Okay? So in the C code, I have to implement this. This is where you would do your audio processing. This example is just simply filling buffers. It's not doing anything fancy. And then there's a play API that we invented that just says, you know, run it. That's all it does. So this really is the simple version of sound. It's you know, very straightforward. What's interesting about this, though, is that we want to decode WAV files, and there's open source code out on the internet that does that. So because this is native client, and because it's in a sandbox, and because we have this special tool chain that does all the security features and the validating and everything else, I can just go and get code from the internet and compile it and run it. It's not, doesn't have to be subject to endless security reviews and things like that. Because if the code from the internet is malicious, it's not going to run, right? It either won't pass the validator, or it'll halt in the execution stage, or something. So I feel pretty confident in just getting random code off the internet, which is normally an extremely unsavory thing to do. But in this case, not a problem. Of course, I'm going to Stanford, and I'm hoping that Stanford is kind of a respectable institution, and they, you know, produce code that's not going to do something nasty. But you know, so here, this is all just C code. It's very, very straightforward, you know, decode WAV files. The other thing I have to do is actually get the sound resource, right? So this is an HTTP request, and we have Pepper API to do that too. So I just simply say I want to open a request, and I set it up as a GET request. You know, I want to follow redirects. In here I can also give it hints about cores and things like that. And then as the data comes in, I read the response body and fill a buffer, and that buffer goes into the previous audio playback thing you saw earlier. Just simply copies it into the sound buffer and plays it. So it's that straightforward. All right, let's see what that looks like. Open an incognito window. Let's go into stamp mode, and if my sound is playing. Okay, so now, and I cleverly got some other sounds in here too, so. Okay, so there it is, the 4 stages of life. All together, you get a pretty good feel of what we can do. Coming attractions are, we are doing an interactive debugger and integrating it with your favorite IDE. We're starting with Visual Studio. Eventually, we'll get to other IDEs, Xcode, Eclipse, et cetera, GWT, integration, that kind of thing. So, but we're starting with Visual Studio because a lot of client programmers are already there. We are doing things like garbage collection, JIT support. We have a port of Mono that runs C#, and we are adding dynamic library support as well. So this will reduce the size of the binaries that you build, right? We're doing Pinnacle, which is a portable library for us. We're using LLVM bitcode format on the wire. And that means that you only have to build one NACL module. The promise being that 10 years from now, someone's going to invent a new CPU architecture, and we want to be able to take Nexes that exist on the web and run them on those too. So What's required is a translation, kind of the final compilation translation stage to actual machine code from the bit code. We're adding more HTML5 support. So generally speaking, we track HTML5. We're going out the door with the 2D and the sound and some event handling and things like that, then quickly followed by 3D and then peer-to-peer and file I/O. And as HTML5 spec starts to mature and grow, we will track it. Some attributions, of course, is Conway's Game of Life basic algorithm. Greg Vertz out in the Boulder office helped me with the graphics and UI design. Wave format comes from Stanford. The doorbell is from Sound Bible, other from WAV source, etc. And where to go from here, we have a doc set. So you can visit Google, code.google.com Chrome native client. And that gives you a full introduction to how to program this stuff. Link to get the SDK. There is an SDK. And a reference for Pepper. And there's all kinds of stuff in there. Some examples. This life example is actually in an open source repo right now. It's called Knackleports. Knackleports contains a bunch of libraries that have been ported to native client. libz, tinyxml, just to name a couple. There's a bunch in there. ImageMagick. SDL has been ported. So if you have an SDL game, there's a Knackle port for that. Visit us in the Chrome sandbox. We've got some demos running. And if there's any feedback for this, there's the tiny URL. Great.
Hi.
Question.
Can you tell us what Google is using this for internally? Or is it in products that we're already using?
It's experimental. It's actually, it's an open source project. What can I say about it? The scientific computing one? Yeah. So that's David Koenig's thing? Yeah. There's a, it runs on app? No? We have a scientific computing project going on within Google. That's about the only one I know of internally. There's a bunch of external ones. There's TCL port was done, and Unity, of course, runs on it. Yeah. SDL port was done. Ah, take one from the front.
One of the reasons to use Knackle is efficient usage for SIMD instructions. Mm-hmm. I noticed that in your manifest there are only CPU architecture, and each of those features several set of SIMDs. So how do we handle this?
That manifest file didn't have absolutely every switch in it. And we're still kind of working out some of those issues. Yeah. But that's an excellent point. Let me take one from the back.
When you were talking about GPU access, were you talking about actual access to hardware rasterizers?
No, it's more OpenGLES2.
Okay, so no, I mean like a hardware card as opposed to
Yes.
a software rasterizer.
Yes,
okay.
absolutely.
So
yes.
Historically, typically we have an elevated group privilege for direct rendering simply because somebody will find out some way to either gain knowledge that they shouldn't have of the system or to make some kind of attack using the hardware. And especially in closed source drivers, it's been a very big problem. So what precautions are you taking to try and mitigate this in Knackle?
We're tracking exactly what WebGL does to solve the same problem.
I should warn you that that's not enough to keep people from potentially gaining information about other processes that are also direct rendering to the same GPU.
Please get on our discussion lists and make your opinions known.
Get on ours, Mesa Dev and DRI Devel at freedesktop.org.
Okay, thanks.
Thank you.
From the front.
Are there any performance hits when running your native code through the sandbox that you've noticed?
Yes, there are. We are generally running between 5 and 10% hit. That's a very broad brush. There are cases, there's degenerate cases where it actually goes faster. But, yes, there is a performance hit. Yeah, back.
So you mentioned that in the sandbox environment, of course, you can't access the file system directly.
Right.
Java virtual machines with signed applets are able to do this still today. And there certainly are some use cases where this is beneficial. For example, developing a web-based video editor or some sort of video manipulation. You wouldn't want to transfer all of that data up to a server and then back down again.
Right.
Is there any kind of strategy that could be used with native client or that you're aware of to sort of accomplish that goal of accessing that local resource without having to transfer it up to the server?
We will track the HTML5 file I/O APIs and implement that within Pepper. So the level of access that gives you is the level of access we'll give you in native client.
Thank you.
Yeah. Okay, Brent.
So from the JavaScript side, the 2D canvas that you were drawing on from NACL, is that data readable, writable from JavaScript like we could do with a 2D canvas? Like getting the raw bytes and reading and writing them as well from JavaScript?
We're working on that.
So it'd be like actually another communication channel kind of between the NACL side and the JavaScript side, reading and writing data in that bitmap.
Correct.
Okay, cool.
Yeah. Okay, next.
So is the idea to move everything eventually to portable NACL? And when you do that, what sort of performance hit will you take additionally if you move to the portable version?
I don't have an answer for that.
Okay.
Yeah, sorry. Next.
Is there support for native sockets?
No, we will support the same level as WebSockets support in terms of actually, opening sockets.
Okay, so basically network
Yeah.
traffic will have to go through the web layer, not through the native code.
Right.
Thank you.
Yeah. Okay.
It might be a silly question, but I'm just wondering, you say it's an open source project. Obviously, it'll be in Chrome. Can we, has there been any interest from other projects like Mozilla to actually get this into other browsers? Is that something that's going to potentially happen? Or as an app dev, I'm wondering if I'm only going to be able to target Chrome users, basically.
We haven't really heard anything. There's absolutely welcome to pick up the code base and make a runtime that works in those browsers. It's, I can't speak for Mozilla and those people. They're, yeah.
Thank you.
Sure. All right, thank you all for coming.